Right now, as you listen to this, light from galaxies nearly as old as time itself is arriving at Earth. Not hypothetically, not in theory, actually arriving. The James Webb Space Telescope, positioned almost 1,000,000 miles from Earth at a gravitationally stable point in space, has spent the last several years collecting this light. And what it has revealed is not what decades of astronomical modeling predicted. Webb has detected fully formed galaxies existing when the universe was barely 300 million years old, systems containing hundreds of millions of solar masses worth of stars, glowing intensely in infrared wavelengths that older telescopes couldn't see. According to the models that guided cosmology for generations, these galaxies shouldn't exist yet. The universe hadn't had enough time to build them, but they're there, measured, photographed, analyzed spectroscopically. Their light has been broken into component wavelengths, revealing not just hydrogen and helium from the Big Bang, but carbon, oxygen, nitrogen, elements that require previous generations of stars to forge and disperse. This isn't speculation, it's data, and it forces a recalculation of how quickly structure can form, how efficiently early gas clouds collapsed into stars, and ultimately, how much of the universe exists beyond the boundary of what we can ever observe. If you enjoy this kind of evidence-based content, where the value is in the voice and the information rather than heavy editing, like the video, subscribe to the channel, and turn on notifications. There are many other videos on the channel built the same way, and if this topic interests you, you'll likely enjoy what's already there. To understand what Webb has revealed, you first have to understand what observation actually means when applied to the universe. In everyday experience, vision feels instantaneous. Light crosses a room so quickly that your brain registers no delay. The time between an object existing and your awareness of it is measured in nanoseconds, far below anything you could notice. But light does not move infinitely fast. It moves at approximately 299,792 kilometers per second. Nothing in the universe travels faster. This speed is absolute, confirmed by countless experiments, woven into the structure of relativity itself. And while it seems fast by human standards, distance can grow large enough that even light becomes a slow messenger. When you look at the moon, you see it as it was 1.3 seconds ago. The sun appears as it was 8 minutes and 20 seconds in the past. If the sun were to vanish this instant, Earth would continue to orbit an invisible point for over 8 minutes before anything changed. The sky would remain bright. Gravity would still hold the planet in its path. Only after that delay would darkness arrive, along with the gravitational disruption. This is not a thought experiment. It's a direct consequence of light's finite speed. Beyond the solar system, delays stretch into years. Proxima Centauri, the nearest star beyond the Sun, is seen as it was 4.24 years ago. The center of the Milky Way, roughly 26,000 light-years away, appears as it was 26,000 years in the past, long before human civilization began. Distance does not simply separate objects in space. It separates them in time. Every photon carries information stamped with the moment it departed. The farther a photon travels, the older that information becomes. This transforms the night sky into a record, not a live image. Every point of light arrives from a different moment in history. But these photons do not arrive unchanged. The universe is expanding, not as matter flying outward into emptiness, but as space itself stretching between galaxies. This was first confirmed in the 1920s when Edwin Hubble measured the velocities of distant galaxies and found that nearly all of them were receding from Earth. The farther away a galaxy was, the faster it appeared to be moving. This relationship, now called Hubble's law, revealed that space itself was growing larger over time. As space expands, it stretches everything moving through it, including light. Wavelengths elongate. Blue light shifts toward red. Red light shifts into infrared. This process, called redshift, is not a visual trick. It's a measurable physical change in the photon's energy. The more stretched the wavelength, the longer the light has been traveling, and the earlier in cosmic history it was emitted. Redshift turns light into a clock. Astronomers measure the redshift of a galaxy's light and use it to calculate how much the universe has expanded since that light was emitted. From that, they infer both the distance to the galaxy and how far back in time they're observing. Distance and time become inseparable. To look deeper into space is to look further back in time. For most of modern astronomy, this created a problem. Early telescopes were designed to observe visible light, the narrow range human eyes evolved to detect. Instruments like the Hubble Space Telescope revolutionized the field by revealing structure, motion, and detail in nearby galaxies. But as astronomers pushed their observations closer to the beginning of the universe, the cosmos appeared to thin out, not because it was empty, but because its light had changed. The earliest galaxies formed in a hotter, denser universe. Their light began as energetic ultraviolet and visible wavelengths, but as it traveled across billions of light-years of expanding space, that light was stretched far beyond visible wavelengths. By the time it reached Earth, much of it existed only as infrared radiation. To visible light telescopes, these regions looked dark. The darkness was deceptive. It was not absence. It was invisibility. The James Webb Space Telescope was built specifically to solve this problem. From the start, Webb was designed as an infrared observatory. Its primary mirror spans 6.5 meters, composed of 18 hexagonal segments coated in gold. Gold was chosen because it reflects infrared light with exceptional efficiency. But mirror size alone doesn't explain Webb's capability. Location matters just as much. Webb does not orbit Earth. It sits nearly 1.5 million kilometers away at a point called the second Lagrange point, or L2, a gravitationally stable location where the combined pull of the Sun and Earth allows the telescope to remain in position with minimal fuel expenditure. This distance allows Webb to do something essential. It allows the telescope to become cold. Infrared light is closely linked to heat. Any warm object glows in infrared. A telescope that is even slightly warm would overwhelm the faint cosmic signals it's trying to detect. So Webb was engineered to disappear thermally. A massive 5-layer sunshield, roughly the size of a tennis court, blocks heat and light from the Sun, Earth, and Moon. On the shadowed side, the telescope's instruments cool to around 40 Kelvin, about -233 degrees Celsius. At these temperatures, the telescope's own thermal glow fades into the background, leaving only the faint whispers of ancient light. Only in this extreme cold can the early universe be observed clearly. When Webb points at a patch of sky that appears empty to other telescopes, it is not searching for nothing. It is waiting for photons that began their journey billions of years ago. Photons stretch thin by expansion, weaken by time, arriving slowly, sometimes one at a time. Webb may observe the same region of sky for days, patiently collecting ancient light that has crossed nearly the entire observable universe. Each photon carries information from a moment that can never be repeated. When those photons are finally assembled into an image, the result is not what early cosmology expected. The early universe does not appear dim or fragile. It appears active. Galaxies emerge when none were predicted. Systems are already forming stars at remarkable rates. Structures are assembling quickly. Instead of a quiet, gradual beginning, Webb reveals a universe that was busy from the start. One of Webb's most striking discoveries involves galaxies observed when the universe was less than 500 million years old, barely 3% of its current age. According to long-standing models, this era should have been sparsely populated. Gravity needed time to amplify tiny density fluctuations left over from the Big Bang. Gas needed time to cool and collapse. Dark matter halos needed time to grow massive enough to trap ordinary matter. Stars required millions of years to ignite. Galaxies, when they finally appeared, were expected to be small, dim, and fragile, collections of stars just beginning to assemble, taking hundreds of millions of years to mature. What Webb found was different. Bright galaxies appeared again and again in these early epochs, not as rare anomalies, but as a recurring pattern. These systems were not barely holding together. They were already forming stars at extraordinary rates, pouring out light in quantities that should have required far more time to produce. Some of these early galaxies appeared to contain hundreds of millions, even billions, of solar masses worth of stars. According to models, assembling that much material should have taken far longer than the universe had existed at the time the light was emitted. What made the discovery even more unsettling was not just how bright these galaxies were, but how chemically evolved they appeared to be. Webb detected spectral signatures of elements like carbon, oxygen, and nitrogen in some of these early systems. Those elements are not remnants of the Big Bang. They're forged inside stars. Carbon forms in stellar cores. Oxygen emerges from massive stars when they explode as supernovae. Nitrogen requires even more processing through multiple stellar generations. Their presence means something unavoidable. At least one earlier generation of stars must have already formed, lived, and died, all within the universe's first few 100 million years. This compresses cosmic history dramatically. It suggests the universe raced through phases astronomers assumed would unfold slowly. When astronomers calculated how much total starlight should exist in the universe's first billion years based on their models, their predictions consistently fell short of what Webb was detecting, sometimes by a factor of 2, sometimes by much more. This was not a small discrepancy that could be dismissed. It was a signal that something fundamental in the models might be incomplete. Scientists responded cautiously. They questioned whether the galaxy's brightness had been misinterpreted. Could dust be affecting the measurements? Could gravitational lensing be magnifying distant galaxies, making them appear brighter and more massive than they truly were? Those effects exist, and accounting for them helped reduce the most extreme cases. But they did not erase the pattern. Again and again, Webb observed different regions of the sky using different instruments and wavelengths. Each time, the early universe appeared crowded and luminous. Star formation was not struggling to begin. It was thriving. This forced astronomers to re-examine one of their most basic assumptions: how efficiently the universe can turn gas into stars. In the present-day universe, star formation is surprisingly inefficient. Most of the gas inside galaxies never becomes stars. It is heated, stirred by turbulence, pushed away by radiation, or blown out by stellar winds and supernova explosions. Only a small fraction collapses into new stars. The early universe appears to have operated under different rules. One possibility is density. Early on, the universe was smaller and matter was packed more tightly together. Gas clouds collided more often, increasing the chances of gravitational collapse. Another possibility is composition. The first generations of stars formed from almost pure hydrogen and helium, without heavier elements to complicate the cooling process. This may have allowed gas clouds to collapse more efficiently. Mergers likely played a major role as well. In the young universe, galaxies were closer together and collisions were frequent. When galaxies merge, gas is driven inward, compressed to extreme densities, igniting intense bursts of star formation. Each of these factors helps explain part of what Webb observes. None explains all of it. At the centers of many of these early galaxies lies another mystery that deepens the tension: black holes that appear far too massive for their age. Webb has detected evidence of supermassive black holes already in place when the universe was less than 500 million years old. Some of these objects weigh millions, even billions of times the mass of the Sun. According to conventional models, this should be extremely difficult. Black holes formed from collapsing stars begin small, typically only tens of solar masses. They can grow by consuming surrounding matter, but that growth is limited. As material falls toward a black hole, it heats up and releases enormous energy, producing radiation that pushes additional matter away. This creates a natural speed limit on black hole growth, called the Eddington limit. Yet Webb keeps finding early black holes that seem to have grown past that limit with ease. To explain them, astronomers have been forced to consider scenarios once thought exotic. Perhaps some black holes formed through the direct collapse of massive gas clouds, skipping the stellar phase entirely and beginning their existence with thousands or even millions of solar masses. Perhaps the first stars were far more massive than those we see today, hundreds of times the mass of the Sun, collapsing into larger black holes from the start. Perhaps the early universe simply allowed growth to happen faster because gas was denser and accretion was more efficient. None of these ideas has yet been confirmed. None can be ruled out. What is clear is that these early black holes are not rare exceptions. They appear alongside the luminous galaxies Webb keeps finding, suggesting that rapid galaxy formation and rapid black hole growth may be connected. This connection matters because these early galaxies did not exist in isolation. Their radiation reshaped the universe. Their ultraviolet light ionized surrounding hydrogen, transforming the cosmos from a neutral fog into a transparent medium, an epoch called reionization. Their supernovae seeded space with heavy elements. Their gravity began sculpting large-scale structure. If they formed earlier and faster than expected, then the entire timeline of cosmic evolution shifts. Events thought to occur later must be moved closer to the beginning. Processes believed to require long, quiet buildup may instead emerge from extreme early conditions. The deeper Webb looks, the harder it becomes to ignore the pattern. The early universe does not appear tentative or slow. It does not behave like a careful construction project. It behaves like a surge. matter collapsed rapidly. Stars ignited efficiently. Galaxies assembled quickly. Black holes grew alongside them. Complexity emerged early, not late. This realization carries an important implication for the scale of the universe. If structure formed so efficiently near the limits of our vision, then the regions beyond those limits, regions we can never observe, may be just as rich, just as complex, and just as crowded with galaxies. The universe did not waste time. And if it was already building this much this early within the observable horizon, then the true scale of what exists beyond that horizon becomes even more difficult to grasp. For much of the 20th century, astronomers believed they were closing in on an answer to one of the largest questions humanity could ask: how many galaxies exist in the universe? The approach was conceptually simple, even if demanding in execution. Aim a powerful telescope at a patch of sky that appears empty. Count every galaxy visible in that tiny region. Then assume that patch is representative and scale the number up to cover the entire sky. When the Hubble Space Telescope carried out its deepest observations, exposures lasting hundreds of hours on regions of sky no larger than a grain of sand held at arm's length, the result was already astonishing. Thousands of galaxies appeared in that tiny frame. From those images, astronomers estimated that the observable universe contained a few 100 billion galaxies. The number was so large it barely felt meaningful. For years, it stood as the accepted scale of cosmic abundance. Then the James Webb Space Telescope looked into similar darkness and quietly complicated everything. Where earlier deep-field images showed gaps between distant smudges, Webb revealed faint structures layered behind one another. Entire populations of galaxies emerged, not because they were newly created, but because their light had shifted into infrared wavelengths older telescopes could not see. This was not a correction at the margins. It was a multiplication. Webb's deep-field observations transformed what empty space means. Regions once thought to contain a few dozen faint galaxies now appear crowded, filled with overlapping generations of systems stretching back nearly to the beginning of time. In one of its most ambitious deep surveys, Webb observed a patch of sky only slightly larger than 3 full moons placed side by side. Over hundreds of hours, it collected faint infrared photons, stacking exposure upon exposure, building an image from light that had traveled billions of years. When the data were combined, the scale of what emerged was staggering. Hundreds of thousands of distinct galaxies filled the frame. Not stars, galaxies. Each one a system containing millions, billions, sometimes trillions of suns. Many host planetary systems. Many have already undergone multiple generations of stellar birth and death. Many are rich in dust and heavy elements forged over cosmic time. The universe, it turns out, is not sparsely populated with isolated islands drifting through darkness. It is densely packed. What makes Webb's contribution especially powerful is not just the sheer number of galaxies it reveals, but the information it extracts from each one. Webb does not merely detect points of light. It measures their colors across multiple infrared wavelengths, allowing astronomers to estimate distances, masses, star formation rates, and approximate ages. Each galaxy becomes a data point in a vast timeline. When scientists began assembling those data points, another pattern emerged, one that had been predicted for decades but never observed with this level of clarity. Galaxies are not scattered randomly. They cluster. They align. They trace enormous structures across space, forming long filaments that stretch tens and hundreds of millions of light years. These filaments intersect at dense nodes where galaxy clusters form, while vast regions between them contain almost nothing at all. This structure is known as the cosmic web. Earlier telescopes had hinted at it. Webb reveals it. Entire populations of dusty galaxies invisible to visible light suddenly fill in the gaps, connecting filaments that once appeared broken. The web becomes continuous, intricate, and unmistakable. This structure is not decoration. It is a record of how the universe evolved. After the Big Bang, matter was distributed almost uniformly through space, with tiny variations in density imprinted during the universe's earliest moments. Regions that were slightly denser exerted slightly stronger gravitational pull. Over time, matter flowed toward those regions, amplifying the differences. A useful analogy is rainfall on uneven terrain. Water does not fall only into rivers. It falls everywhere. But gravity pulls it downhill, carving channels and valleys while leaving high ground dry. Over time, a structured landscape emerges. In the universe, gravity played the same role. Matter flowed into filaments and nodes, draining surrounding regions and leaving behind vast voids. Webb's observations show that this process began early. Filaments tens of millions of light-years long already existed when the universe was only a few billion years old. Some structures appear surprisingly organized for their age, challenging assumptions about how quickly matter can arrange itself on such large scales. One striking example is a structure stretching over more than 10 million light-years, discovered in the early universe. A chain of galaxies lying along a single filament, connected like beads on a cosmic string. Several of its largest members have already stopped forming stars, an unusual state for such early times. This suggests that environment plays a critical role. Galaxies growing in dense regions evolve differently from isolated ones. Frequent interactions and mergers accelerate their life cycles. Gas is consumed quickly. Star formation can shut down early. Webb has allowed astronomers to identify thousands of galaxy groups and protoclusters across cosmic time, tracing how small associations of galaxies grow into the massive clusters we see today. By comparing groups at different distances, scientists can effectively watch structure formation unfold across billions of years. This continuous view was not possible before. Yet for all this density and organization, the universe is also defined by emptiness. Between the filaments of the cosmic web lie enormous voids, regions tens to hundreds of millions of light-years across that contain very few galaxies. These voids are not small gaps. They dominate the volume of the universe. If you could stand at the center of one and look in any direction, you would see darkness stretching for tens of millions of light-years before encountering the nearest galaxy. Entire regions of space failed to gather matter simply because gravity pulled that matter elsewhere. Webb's deep field images capture this contrast vividly. Dense knots of galaxies appear alongside yawning dark regions containing almost nothing at all. The universe is crowded and empty at the same time. This duality reshapes how astronomers think about scale. Counting galaxies is no longer just about tallying objects. It is about understanding distribution, clustering, and the vast spaces between. When astronomers extrapolate Webb's deep field counts across the entire sky, the numbers change dramatically. The total number of galaxies in the observable universe may not be in the hundreds of billions. It may be in the trillions. That increase has profound implications. More galaxies mean more stars. More stars mean more planetary systems. The universe becomes not just larger in size, it becomes richer in possibility. Yet even this abundance exists only within the observable universe, the region of space from which light has had time to reach us since the beginning of cosmic history. Beyond that boundary, space continues. Structure continues. Galaxies continue to form and evolve. Webb's deep fields hint at this by showing that even near the limits of our vision, the universe remains densely populated. There is no sign of thinning toward an edge. This raises a crucial point. If reality is this crowded within the portion we can observe, then the true scale of everything beyond it may be vastly larger than even our most generous estimates. Counting the uncountable does not give us a final number. It reveals how incomplete our perspective truly is. Webb has not finished the census of the universe. It has shown us that the census may never end, and that what we once thought was nearly complete may only have been the beginning. At first glance, the universe seems like it should be easy to measure. The Big Bang happened roughly 13.8 billion years ago. Light travels at a fixed speed. It feels natural to assume that the most distant objects we can see should be about 13.8 billion light-years away. That intuition is deeply misleading. The observable universe is far larger than its age would suggest. Its radius is not 13.8 billion light-years, but closer to 46 billion light-years, giving it a diameter of roughly 93 billion light-years. This is not a speculative number or a trick of language. It is a consequence of how space itself behaves. The confusion comes from how we picture motion. Nothing can move faster than light through space. That rule still holds. No galaxy is breaking a cosmic speed limit. No signal is outrunning physics. Instead, the universe grows in a quieter and far stranger way. Space itself expands. When astronomers say distant galaxies are moving away from us, it's tempting to imagine them flying outward like debris from an explosion. But on cosmic scales, galaxies are not traveling through space away from a central point. They are being carried apart as the space between them stretches. A simple analogy helps clarify this. Imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves farther away from every other dot, not because the dots are sliding across the surface, but because the surface itself is expanding. No dot sits at the center. None is special. Every dot sees all others moving away. The universe behaves in much the same way. When a distant galaxy emitted the light we observe today, it was much closer to us than it is now. Over billions of years, while that light was traveling toward Earth, the space between us and the galaxy expanded continuously. By the time the light arrived, the galaxy that emitted it had been carried tens of billions of light years farther away. This is why we can see galaxies whose light has been traveling for more than 13 billion years, even though their current distance is far greater than 13 billion light years. Light is not crossing a static distance. It is moving through a distance that grows while it travels. In effect, light is running on a cosmic treadmill. Early in the universe's history, expansion was slower, and light made steady progress. As time passed, expansion accelerated, stretching distances faster and faster. Some photons managed to reach us because they began their journey early enough. Others never will. This creates a boundary, not a wall, not an edge, but a horizon. The cosmic horizon marks the limit of what can ever be observed from our location in space and time. Beyond it, light cannot reach us, not because it runs out of time, but because the space it must cross grows faster than light can traverse it. And this is where the scale of the universe becomes unsettling. Space does not end at the cosmic horizon. We know this because the universe looks essentially the same in every direction we observe. The number of galaxies does not thin toward an edge. The faint afterglow of the early universe, the cosmic microwave background, appears nearly uniform across the sky. That uniformity would be difficult to explain if space abruptly stopped just beyond our view. So the universe extends beyond what we can see. But it extends in a way that permanently hides much of itself. Beyond the observable horizon, galaxies still exist. Stars continue to form and die. Black holes merge. Entire cosmic histories unfold in regions that will never influence us and can never be influenced by us. No signal from those regions will ever reach Earth, not because our instruments are limited, but because space-time itself prevents the information from arriving. Even more strangely, this boundary is not fixed. As time passes, the observable universe grows because light from more distant regions has had more time to reach us. The horizon slowly creeps outward. At the same time, the expansion of space is accelerating, causing distances to stretch faster now than they did in the past. These two effects compete. The result is a universe where some objects briefly become observable, only to later slip beyond reach forever. Galaxies we can see today are not guaranteed to remain visible indefinitely. Their light continues to stretch, shifting into longer wavelengths, becoming thinner and more diluted with time. From our perspective, those galaxies appear frozen at a particular moment in their history. We see them as they were, not as they are becoming. Their later evolution, their mergers, their transformations, their eventual fate, may be information that will never arrive. This is not a distant abstraction. It follows directly from measured expansion rates. If the universe continues behaving as it does now, then in roughly 100 billion years, every galaxy outside our local gravitationally bound region will cross the cosmic horizon. Future observers would see a universe containing only a small cluster of nearby galaxies surrounded by darkness. They might never know that anything else ever existed. This changes the meaning of observation itself. The observable universe is not the universe. It is the portion of the universe that happens to be observable from where we stand at this moment in cosmic time. Move to another galaxy, and the observable universe changes. Different regions enter view while others disappear beyond the horizon. Every location in space defines its own observable bubble. This leads to strange but unavoidable consequences. Two galaxies can both be visible from Earth yet unable to see each other. They may lie on opposite sides of our horizon. Light from both reaches us, but light from one can never reach the other. From their perspectives, Earth itself may lie beyond their cosmic horizon. There is no privileged vantage point, no center, no place from which the entire universe can be seen at once. Every observer sits at the center of their own observable universe, bounded by limits set by expansion and time. This is why pushing deeper into space matters. Each new detection near the horizon is not just a discovery of another galaxy. It is a confrontation with the limits of knowledge itself. The galaxies Webb detects at extreme distances are no longer where their light began. They have moved far away while that light was in transit. What we observe is a historical imprint, not a current location. What we see is not what is, it is what was. Beyond the observable horizon lies the unobservable universe, regions that may contain structures just as rich and complex as those we can see. Some models suggest the universe may be infinite. Others suggest it is finite but unimaginably vast. Either way, the observable universe is almost certainly only a fraction of the whole. James Webb has not revealed the edge of the universe. It has revealed that there is no accessible edge at all, only a horizon that keeps moving and a reality that extends far beyond anything light can ever bring to us. In the 20th century, cosmology rested on a simple expectation. The universe began in the Big Bang, expanded outward, and gravity immediately went to work trying to slow that expansion down. The great unanswered question was not whether gravity mattered, but whether it would eventually win. Would the universe expand forever, thinning into darkness, or would gravity one day reverse the process, pulling everything back together? Every version of that debate shared the same assumption: gravity was in control. That assumption did not survive observation. In the late 1990s, astronomers began studying distant stellar explosions known as Type Ia supernovae. These events occur when a white dwarf star in a binary system accretes matter from a companion until it reaches a critical mass, approximately 1.4 times the mass of the Sun, and detonates in a thermonuclear explosion. Because this mass threshold is consistent, Type Ia supernovae produce explosions with nearly the same intrinsic brightness every time. This consistency makes them cosmic standard candles. By measuring how bright one of these explosions appears from Earth, astronomers can calculate how far away it is. Combine that distance with how fast the host galaxy is receding, and the expansion history of the universe begins to reveal itself. What the data showed was not subtle. Distant supernovae were dimmer than expected. Their host galaxies were farther away than they should have been if cosmic expansion was slowing under gravity's pull. The universe was not decelerating. It was accelerating. The farther astronomers looked, the clearer the pattern became. Expansion had not merely continued since the Big Bang, it had been speeding up for billions of years. Something was pushing space apart, overpowering gravity on cosmic scales. To account for this behavior, cosmology was forced to introduce a new component into its equations: dark energy. Dark energy is not something we see directly. It does not shine, reflect, or absorb light. It does not clump into stars, planets, or galaxies. We infer its existence entirely from its effect on space itself. And that effect dominates the universe. Measurements indicate that dark energy makes up roughly 68% of the total energy content of the cosmos. Ordinary matter, everything familiar, from atoms to galaxies, accounts for less than 5%. Dark matter makes up most of the remainder, around 27%. The universe we can see is a minority presence in its own story. What makes dark energy especially unsettling is how it behaves as the universe expands. Normal matter thins out as space grows. Double the volume of space, and the density of matter drops by half. Radiation thins out even faster. Dark energy does not follow this rule. Its density appears to remain constant even as space expands. This means that as the universe grows larger, the total amount of dark energy increases. More space creates more dark energy, and more dark energy drives faster expansion, which creates even more space. It is a quiet feedback loop. For the first several billion years after the Big Bang, matter dominated the universe. Gravity sculpted structure, pulling matter into galaxies, clusters, and filaments. Expansion continued, but it slowed slightly as gravity resisted it. Then, about 5 billion years ago, the balance shifted. As matter became increasingly diluted by expansion, dark energy overtook it. From that point on, expansion began accelerating, and gravity's influence on cosmic scales began to weaken. The universe entered a new phase. The James Webb Space Telescope does not detect dark energy directly, but its fingerprints are everywhere Webb looks, in the extreme stretching of ancient light, in the immense size of the observable universe, and in the way distant galaxies fade and recede. The influence of dark energy is written across the sky. Without dark energy, the universe would be far smaller. The cosmic horizon would lie much closer, and vast regions of space we can observe today would never have entered our view. Dark energy does not just shape the present, it determines the future. If dark energy remains constant, as current observations suggest, then expansion will continue forever. Gravity will still hold galaxy clusters together, but everything beyond them will gradually drift away, crossing the cosmic horizon one by one. Trillions of years from now, observers inside a galaxy like the Milky Way would see a universe filled with nearby stars and very little else. The cosmic web would disappear beyond view. The evidence of the Big Bang itself would fade, stretched into wavelengths too long to detect. The universe would still exist, but it would appear almost empty. This alone would be unsettling. But Webb has sharpened an even deeper problem. When astronomers measure how fast the universe is expanding today, they do not get a single answer. They get two. One method looks far into the past, studying the cosmic microwave background, the faint afterglow released when the universe was only about 380,000 years old. From subtle patterns in that radiation, scientists infer an expansion rate of about 67 kilometers per second per megaparsec. The other method looks at relatively nearby objects. Astronomers measure distances to galaxies using variable stars called Cepheids and Type Ia supernovae, then compare those distances to how fast the galaxies are receding. This approach consistently produces a higher value, around 73 kilometers per second per megaparsec. Both measurements are precise. Both have been repeated using independent methods. Both have been scrutinized extensively. But they do not agree. This discrepancy is known as the Hubble tension, and it represents one of the most serious unresolved problems in modern cosmology. The expansion rate sets the universe's age, its size, and its future. If we are misunderstanding it, then many conclusions drawn over decades may need revision. James Webb was expected to help resolve this tension by refining distance measurements, particularly those involving Cepheid variables used to calibrate cosmic distances. Instead, Webb confirmed the higher expansion rate. The tension did not fade, it hardened. This leaves cosmology facing uncomfortable possibilities. There may be an unknown systematic error hiding in the data. Our assumptions about the early universe may be incomplete. Or there may be new physics at work that we have not yet discovered. One possibility is that dark energy is not truly constant, that its strength changes over cosmic time. Another is that the early universe behaved differently than we assume, leaving subtle imprints that still affect expansion today. Each possibility carries profound consequences. If dark energy evolves, then the future of the universe could look very different from current expectations. In extreme scenarios, dark energy could grow stronger over time, eventually overwhelming gravity even on smaller scales. In the most dramatic versions of this idea, expansion would not stop at separating galaxies. Galaxy clusters would be pulled apart. Galaxies themselves would dissolve. In the farthest future, even atoms could be torn apart in an event sometimes called the Big Rip. Current evidence does not favor this outcome. But uncertainty remains. What is already clear is that dark energy dominates the cosmos. It stretches space, hides vast regions of reality beyond every horizon, and determines what future observers will be able to see and what they will never know existed. It is the reason the observable universe spans nearly 93 billion light-years. It is the reason most of reality will forever remain inaccessible, not just technologically, but fundamentally. And yet dark energy alone cannot explain the universe we observe. Because while it pulls space apart on cosmic scales, something else must pull matter together on smaller ones. Something must allow galaxies to form instead of dissolving into uniform emptiness. That force is also invisible, equally mysterious, and just as essential to understanding how structure can exist in a universe being relentlessly stretched apart. If dark energy governs how the universe expands, then dark matter governs how it holds itself together. Without dark matter, the universe revealed by the James Webb Space Telescope would not exist in any recognizable form. Galaxies would never have assembled. Clusters would have dispersed. The large-scale patterns traced across the cosmos would never have emerged. Dark matter does not shine. It does not absorb light. It does not emit radiation of any kind we can directly detect. And yet it outweighs everything we can see by more than 5 to 1. Roughly 85% of all matter in the universe is dark matter. Everything familiar, stars, planets, gas, dust, makes up only a small remainder. What we see is not the structure itself. It is the illuminated surface of something deeper. The first hints of dark matter appeared long before modern telescopes existed. In the 1930s, astronomer Fritz Zwicky studied the motion of galaxies inside the Coma cluster and noticed something strange. The galaxies were moving far too fast to be held together by the visible matter alone. According to his calculations, the clusters should have flown apart long ago. Yet it remained bound. Zwicky proposed that some unseen mass must be providing the additional gravity. He called it dark matter. For decades, the idea was largely ignored. Then, in the 1970s, astronomer Vera Rubin and her colleagues made detailed observations of spiral galaxies, measuring the velocities of stars at different distances from the galactic center. They expected to find that stars farther out would orbit more slowly, just as outer planets in the solar system orbit more slowly than inner ones. Instead, they found that stars in the outer regions moved just as fast as those closer in. The rotation curves were flat, not declining. This indicated the presence of a massive, invisible halo of matter extending far beyond the visible disk of each galaxy. Gravitational lensing offered further evidence. Light from distant galaxies bends as it passes massive objects on its way to Earth, a phenomenon predicted by Einstein's general relativity. In many regions of the sky, that bending was far stronger than visible matter could explain. Space itself was curving around mass that could not be seen. Dark matter was not a theoretical convenience. It was unavoidable. What makes dark matter so influential is not just how much of it exists, but how it behaves. Unlike ordinary matter, dark matter does not collide with itself or lose energy by emitting radiation. It passes through space almost without friction, interacting primarily through gravity. This simple difference had enormous consequences in the early universe. Shortly after the Big Bang, the universe was hot, dense, and nearly uniform. Ordinary matter was tightly coupled to radiation, resisting collapse. Dark matter was not. Free from that interaction, it began clumping first, responding to tiny density variations imprinted during the universe's earliest moments. These clumps grew into massive halos, vast, invisible concentrations of mass spread throughout space. As the universe cooled, ordinary matter began to fall into these dark matter wells. Gas collected, compressed, and heated. Eventually, nuclear fusion ignited, and the first stars were born. Over time, those stars assembled into galaxies, not randomly, but precisely where dark matter had already shaped the terrain. The visible universe traces an invisible blueprint. This process produced one of the most striking features of reality, the cosmic web. On the largest scales, matter is arranged into long filaments stretching tens and hundreds of millions of light years. These filaments intersect at dense nodes where galaxy clusters form, while vast voids open between them, containing very little matter at all. This structure is not decorative. It is the outcome of gravity acting over billions of years. For decades, the cosmic web existed mainly in computer simulations. Scientists modeled how dark matter should clump and evolve, predicting filaments, nodes, and voids long before telescopes could confirm them. Observations hinted at the pattern, but much of it remained incomplete. James Webb changed that. By detecting faint, distant galaxies that earlier surveys missed, Webb filled in gaps in the cosmic map. It revealed how early these filaments formed and how strongly they influenced galaxy growth. Structures once thought to require long periods of cosmic evolution were already in place when the universe was still young. Galaxies do not grow in isolation. They grow along filaments. Gas streams through space like traffic along cosmic highways, guided by gravity into galaxies where it fuels star formation. When galaxies lie at intersections of multiple filaments, growth accelerates. When they fall into dense clusters, their evolution changes again. Webb has captured galaxies caught in these environments, revealing how structure shapes destiny. Some galaxies are stripped of gas as they move through clusters, shutting down star formation. Others experience intense bursts of activity as mergers compress their gas. Environment matters. The universe is not just expanding randomly. It is organized and interconnected on scales far beyond human intuition. Perhaps the most compelling confirmation of this invisible architecture comes from gravitational lensing on large scales. By measuring subtle distortions in the shapes of distant background galaxies, astronomers can map the distribution of mass even when that mass emits no light. These maps reveal dark matter stretched across space, threading between galaxy clusters along filaments. Dark matter is not confined to galaxies alone. It connects them. The cosmic web is not metaphorical. It is physical. At the densest nodes of this network lie galaxy clusters, the most massive gravitationally bound structures in the universe. These clusters act as anchors, pulling matter inward along filaments, growing over time as more material falls in. Within these clusters, galaxies are transformed. Gas is heated or stripped away. Star formation slows or stops. Shapes become smoother. Interactions become more frequent. Webb's infrared vision allows astronomers to observe these transformations in detail, even in the distant universe. The cosmic web is not static. It evolves. Filaments thicken. Clusters grow. Voids expand as matter drains away. The universe rearranges itself continuously under gravity's influence, even as dark energy stretches the fabric of space on larger scales. This creates a fundamental tension. Dark matter builds structure. Dark energy pulls it apart. On smaller scales, gravity wins. Galaxies form. Clusters remain bound. On larger scales, expansion dominates, separating regions of space faster than gravity can overcome. The universe exists in a delicate balance between these two unseen forces. Despite its central role, dark matter remains one of the greatest unsolved mysteries in physics. We do not know what it is made of. It does not match any known particle in the standard model of particle physics. Decades of experiments have searched for it directly, so far without success. And yet its influence is undeniable. Remove dark matter from the equations, and the universe collapses into incoherence. Galaxies cannot form. Structure cannot emerge. The cosmos becomes a nearly uniform haze, expanding smoothly but building nothing. James Webb does not solve the dark matter mystery, but it reinforces its necessity by revealing how quickly structure formed in the early universe. Webb shows that visible matter alone could never have done the job. Dark matter provided the scaffolding, the head start that allowed complexity to arise so early and so efficiently. And this brings the story full circle. The universe revealed by Webb is not just larger than expected. It is more interconnected, more structured, more dependent on invisible forces than we once imagined. What we see, stars, galaxies, glowing clouds, is only the surface layer. Beneath it lies an unseen framework shaping everything. And even this vast, interconnected universe represents only what we can observe from our position in space and time. Beyond every horizon, the same forces continue their work. Dark matter still builds. Dark energy still stretches. Galaxies still rise and fall in regions we will never see. The true scale of the universe is not just measured in light years. It is measured in how much of reality operates beyond our senses, beyond our instruments, and beyond our reach. James Webb has shown us that the universe is not a simple place made only of what shines. It is an architecture of the invisible, vast, ordered, and extending far beyond the limits of what light can ever bring to us. If you appreciate this kind of clear, evidence-driven explanation, subscribing and liking the video helps more of this content reach the right audience. You'll also find many other videos on the channel that follow the same approach.